Hello, everyone. Welcome to our AWM seminar Pittsburgh chapter. And today is our last seminar for the semester. Thank you so much for joining us and support us. So our speaker today is Anusrika Datta. She's from the University of Tennessee, Knoxville, and her talk is the introduction to the Drury Arveson space and its multipliers. Anusrika, please go ahead.
Thank you for introducing me and thank you for having me today. So, my talk is actually based on introducing a new kind of space that's a Dewey Arveson space. And I'm going to talk about something about its multipliers too. Uh, then, whenever we see that kind of talk the title, the first thing that comes to our mind is like why do we need a different kind of space, right? So that's the main thing what we have. So first thing, I think so. Okay, sorry. Okay. So, whenever we see that kind of title, so the first thing that comes to our mind is like, why do we need the another space? Like we have a lot of spaces already in the list. So why do we need another space? So that's why first at the very beginning, I'm going to give you a background, like why we need such a space and like how Drury and Arveson both come to the point where they introduce the space. And then I'm going to give us formal definition, and then I'm going to say what is multipliers and why we actually talk about multipliers. So the first thing, the story of Drury-Arveson space actually goes back to the von Neumann inequality for contraction. Now, what is a contraction? A linear operator T on a Hilbert space H is called contraction if the operator norm is bounded. Now, what the von Neumann inequality actually says, like if we have a contractive operator on a Hilbert space, then if we take the norm of, like if we have a one variable polynomial P, and if we take the norm of P of T, that should be bounded by supremum of the absolute value of P on the disk or on the unit ball. As an immediate consequence, you can see that the right-hand side actually is the supremum norm of like the sup norm, or you can say the L infinity norm. Now, the first thing that comes to our mind seeing this kind of inequality for one variable polynomial is that, like, can we generalize it? Like, do we have any similar inequality for the multivariable polynomial or not? So before we jump into answering that question, first let me say some example like why we are motivated to do that. So first consider an unilateral shift operator where we are shifting our coordinate just by a position. So we are having a0, a1 with all the coordinates, and we are just shifting that, taking the first coordinate as 0. And then we are considering a map Q from L2 to a Hilbert space. Here specifically, we can think about it's the Hardy space. I know it's not a known space to all of you, but like you can say that the Hardy space is somehow where Hardy space is a function of holomorphic functions where the coefficients of the power series are square summable. Like you can think like that, those spaces. So we are taking L2 to those Hilbert spaces defined by where we are taking all the sequences to its power series where the coefficients of the power series are square summable. So this is my U map and this is my L map. Now we want to consider the composition of U and S. So if we take U compose S, then we are going to get this power series where we have the shifted coefficients. Just the coefficient shifted by 1. Now let's introduce another multiplicative operator mz, which is again from Hardy space to the Hardy space. And what mz actually does is, like, if you take any function on the Hilbert space, then if you apply mz, or mz takes that to multiplying the z with the function. Like mz of f gives you the z times f. Z is the point or the coordinate function. Now, if we take the composition of mz with u, then we are going to see that this will give us the same power series that we have from u composes. So point-wise, mz compose u and u composes are giving us the same thing. So that implies mz with the multiplicative operator with the Hardy space is unitarily equivalent to the unilateral shift operator with L2 space. Now you can see that this makes our life a little bit easier. Like, it's very easier to consider a function of the function on the Hilbert space and see how it is actually behaving under the multiplication rather than the unilateral shift operator. Now, for any polynomial p, if we define p mz of f as the multiplication of p times f, then we can see that the norm of p mz is the subnorm of p. If we take the supremum norm, that means we are taking the supremum norm of f is less equals 1, and that gives you the infinity norm of p by the max modulus principle. It always attains the maximum on the boundary. So that's why we are going to get this inequality. And for any contractive operator t, we have, by von Neumann inequality, norm of pt is less equals this, because on von Neumann inequality we have norm of pt is less equals the subnorm, and here the subnorm is equals the norm of pmz. So we can replace that here and we get this inequality. And this is actually the motivation that we are going to use in a bit. We are going to see that in a bit. Where we'll use this motivation. Okay. So an extraordinary amount of work has been done by the operator theory community extending the inequality of von Neumann actually. So what we can expect is, like, for generalization to the operator tuple. So there we had one operator, contractive operator. So here we are considering n number of operator tuple where T1, we are taking T1 to Tn. They are commuting tuple of operators, and we are considering each of them are a contraction. Then we should expect that this inequality holds, right? Just the similar for the von Neumann's inequality. But what happens is, like, for n equals 2, it's actually true. And in 1963 proves that for n equals 2, this inequality holds. But for n bigger equals 2, bigger equals 3, in 1973, Varopoulos proved that it's not true. He gave a counter example to show that this is actually false for n bigger equals 3. This raises few questions. So let's see the questions. The first thing, what is the right notion of the contraction? So on von Neumann inequality, we had all the operators at the contraction. So here, if we consider that each on the operator tuple of n operator tuple, if each of them are a contraction, that's not helping us. So we have to figure out the right notion for the contraction of commuting tuple of operators. The second thing that you want to think about is a right domain where we can consider the norm such that we can get such an inequality. And the third thing is whether we have any correct notion or the right form of the RHS where we had the subnorm, where can we get anything similar to the subnorm. There is the third question can be actually modified using the motivation that we have got, like the norm of P of mz that was equals the infinity norm. So we get the motivation from that and we can think about like something there. Now, after initial experiments that I am talking about, the subnorm on the RHS, it was quickly like realized that it's not like actually sufficient. So we need a different norm on the RHS, not just the sup norm. It's not helping because for general N is very small value. So it's very hard to get this as an upper bound for any norm. And we need some different concept of a contraction for each, like the each ti on the operator tuple being individually contraction is not enough. So we need some different concept of contraction. So then both Drury and Arveson arrived at the space of which they didn't name the Drury-Arveson space. They just arrived at a space where they can have those modifications. But later they named that Drury-Arveson space, and surprisingly, Drury in 1978 and Arveson in 1998, both of them have arrived at the same kind of space. And because we didn't have that time of the internet access properly, so they didn't know that the work has been done previously. So they individually have done the same work actually. So they consider the generalization of the von Neumann inequality for commuting tuple of operators in operators. And they introduce a notion that's called the row contraction. Now, what's a row contraction? If you have a commuting tuple of operators A1 through AN on a Hilbert space, then that should be said a row contraction if the operator inequality this holds on the Hilbert space. Now, this is where we want to replace the contraction with the row contraction of the operator tuple to get the von Neumann inequality on high dimension spaces. Now, in the setting for such a tuple A1 through AN being commuting row contraction, Drury and Arveson showed that this inequality holds. So the left was the same as the von Neumann inequality, but the right inequality is something different than the sup norm. Here we have arrived in a norm that should be explained to the new space that's called Drury-Arveson space, and I'm gonna explain that in a bit. So for now, just be assured that this inequality holds defined on this space. And these polynomials are any polynomial with complex coefficients, so we can have n or more than n variables.
Can you go back one slide? I just missed something.
Sure.
Okay, so is one here is the identity operator, or?
Yeah.
Okay.
Now, very informally, we can say that the Drury-Arveson space is a space of holomorphic functions on the ball. But to define it properly, first let's see how the inner product on the Drury-Arveson space actually works. So if we have this multinomial power series for age zeta and with the coefficient A alpha, and for G zeta, if we have the power series notion like this with coefficients B alpha, then the inner product of HG is defined like the summation of alpha factorial over modulus alpha factorial A alpha B alpha bar, where these are the multinomial notions, where A alpha factorial means alpha is D variable coordinates, and then alpha is alpha 1, alpha 2, alpha D. Then alpha factorial is alpha 1 factorial multiplied with alpha 2 factorial multiplied with ... alpha D factorial, like that. So this is the definition of the inner product on the Drury-Arveson space. Now we are introducing the reproducing kernel, which is a function that defined by 1 over 1 minus inner product of zeta times z. And we say that this is a reproducing kernel for the Drury-Arveson space because it reproduces your function. What does that mean? If we take inner product of any function on the space with this reproducing kernel for a fixed z, then we are going to have the evolution of the function on that coordinate. Let's see, like I know it's hard to believe that we get this inequality. So let's see how actually it works. So if we take this inner product, H is Kz, the reproducing kernel. Then H is the inner summation of this. This is a power series representation of H. And Kz at zeta is 1 over 1 minus inner product of zeta z. Then we can write this 1 over 1 minus zeta z as this multinomial notion. And if we take the sum out, then we end up with this inner product. And then this inner product is giving us A alpha z to the power alpha. That is the HZ. Okay. Now let's formally define the Drury-Arveson space. So what is the Drury-Arveson space? It's a collection of all those functions, holomorphic functions, which has a power series notion like that, such that the norm of f square, which is defined by this multinomial formula, that is finite. So it's almost like we can say that the coefficient of f is almost square summable, but with a weight on it, not properly like that. That is a formal definition of the Drury-Arveson space. Okay, let's move on to the next, to the multipliers. So one of Arveson's paper, main contribution in 1998 paper is the introduction to the multipliers for Drury-Arveson space. I'm gonna like explain in a bit why we actually, why the multipliers are actually important. But let's first define those. So if any function f on h to d is said to be a multiplier if f times z is in h to d for any z in the h to d. Like for any function on the space, if we multiply that with our required function, then the specific function, then we are going to say that this is a multiplier if it multiply with all the functions on the space and give me the any other function on that space only. And we are going to denote this script m as a collection of all the multipliers on the space. And the multiplication operator is bounded operator, that we can prove that by closed graph theorem also. And on the multiplier operator, we can define the multiplier norm. So for each f in M, we define the multiplier norm as the supremum of all those norm of fz, where G is in the space, the Drury-Arveson space, and G is a contractive operator, or G norm of G is bounded. Then this is the multiplier norm. Now, if you remember when I said the von Neumann's inequality, like the version of the von Neumann's inequality for the higher variable, like higher dimension spaces, so then we had on the right side the norm, which actually the multiplier norm. So here, for getting this inequality, we had to introduce a multiplier norm on the Drury-Arveson space. And for d equals 1, like for one variable case, it actually reverts back to the actual von Neumann inequality, because for d equals 1, the multiplier norm and the sup norm are the same. That we have seen on the example that I have given at the very beginning. Okay. Any questions? Okay. Now, like why we are talking about the multipliers. So one thing is to get the multiplier norm for getting the von Neumann type of inequality for a higher dimensional case. Now we are actually interested in multiplier invariant subspaces. And what is that? Like this is the subspace of any Hilbert space where we can get phi times f, like that satisfies phi times f is in the space whenever we have phi is a multiplier, f is in the subspace. So phi is a multiplier on H. So by the property of the multiplier, phi times f is always in H, but it may not be in N. But if it is in N, then we're going to say that this is multiplier invariant subspace. And if f is in H, we denote by this close like the box F as a closure of phi times F, where phi is a multiplier. We take the closure on the Hilbert space and denotes this as the invariant subspace generated by the F. And if this invariant subspace generated by F gives us the whole space, then we call that function is a cyclic function in H. Now, why am I just defining those random stuffs? Because actually we are interested in the most popular problem in my field, like the functionalist field, that is invariant subspace problem. And I'm going to finish my talk just saying few things about this. So what is the invariant subspace problem, which is open for a long period of time? This is asking you whether every bounded linear operator has a non-trivial closed invariant subspace or not. What does that mean? Like they're asking whether a closed linear subspace W of H, which is different from the empty space or the whole space, then whether TW subset of W holds or not. So as you can see that for cyclic functions, it actually generates the whole space. So we are actually trying to find the non-cyclic functions, which means it will not generate the whole space. It will be a subset somehow or subspace. Then we can say that this inequality, like this inclusion may hold. So we're trying to find the non-cyclic function such that we can have something about this problem. This problem has been studied for a longer period of time, and few specification has been done. It has been proven that it's not true. Like there is a counter example for the Banach space, but for Hilbert space, still the problem is open till now. Though Enflow last year claimed that he has proved that, but it's still under review, so we don't know. Maybe we have a solution, may not be, but still we are trying to have some progress on these problems. And that's all that I have for today.